concerned, you can probably assume about 50 lines or 60 lines is a good limitation of how many characters or how many lines you can fit on one screen. And that isn't worse, right? That makes it even worse because when your single algorithm has 500 lines and you can only display 50 at a time, that means you need 10 page ups and 10 page downs to go from one end to the other end. Even if you use the indentation to help yourself, it's not going to be very helpful because the indentations, the beginning construct is so far off from the end, you can't even keep track of all the indentations in between. Are we kind of understanding the physical limitations, that makes it necessary to do top-down design? But tech, it's okay, because our algorithms will never exceed 50 lines, so there's no problem that our screen only has 50 lines. Is that okay? How many lines are there in a useful program? Easily hundreds of thousands, right? Linux has millions. Most major software like OpenOffice probably has millions of lines also. So that means you cannot just say, well, we just don't write algorithms that requires, more than 50 lines. So now how do you fit millions of lines into 50 lines? In other words, you look at the map here. See, this is nice because we can actually see it graphically. I cannot possibly display every single city and every single town on this map because there are just way too many to display on the map of the United States in general. So what do? Do I say, put a limitation and say the United States can only have up to 50 towns, 50 cities? No, I cannot do that, right? So what do? Exactly. I divide the whole region into bigger chunks first. Okay? So I divide it first into states. Most people organize a country by states or provinces first. Okay, there are only 50 states, and most people can remember approximately where a particular state is at. So let's say whatever I'm trying to find is in, let's say it's in California, which is easy because we all know California. But when you look at the map of California, it does display all the major cities, but not the smaller ones. For instance, let's say I want to go to, Monterey. Okay, if I want to go to a particular street or downtown Monterey, I can't really see Monterey on this map because it is not a big city like San Francisco. So what do? I have to zoom in. Now, as you zoom in, more detail is being shown. Okay, we want something kind of like this in programming too. We want to be able to see just the overall part of an algorithm and be able to zoom in and say, okay, well, this piece, I'm not quite sure how it is done. I want to see how it is done. So this is how you zoom in, and over here you can actually see Monterey already, except I do not see downtown Monterey. I can see the entire town and where it is. So when you zoom in even more, then you can see Monterey is actually zooming, in becoming kind of bigger. And you can zoom in a little more. And where's downtown Monterey? It's not the Presidio. But anyway, if you know the town, you can probably find it, easily at this point. But do you guys understand the whole idea of, even though you have a lot of details to capture or to store, you can control the view so that every single time or with every screen, you only have so many items to search for, to look for. Yeah. Okay, very good. So we want to do the same thing with programming, okay, or about the same thing in programming. The question is, how do we do it? And, how does it work? So that's the question. We'll go ahead and open up this note here, and we'll take a look at how it should be done, or one way to do it. We have just covered Section 2. The entire Section 2 just wants to explain why top-down design is actually useful in real life, and that's basically a map is already a good example. The section 3 with section 3.1, it explains why in terms of algorithm design or programming, why we need to have top-down design. It has to do with the number of lines we can display at any particular time, as well as how many things we can track at any particular time. Now the next question, or the next one, is section 3.2. It explains, but how do we fit a 2 million line programs, into 50 lines? Well, the answer is you cannot. So what you do is you basically use abstraction. One line of the 50 lines can expand into 50 lines, and each one of those 50 lines can expand into 50 lines, and so on and so forth. So that way, you can still manage million lines of code, but each algorithm is only about 50 lines. Okay. So now we have an example. Starting with 3.3, we have a concrete example, and in this case, I will actually start to explain how do you begin, how do you start to write an algorithm, which is a big question, and it is also something that is really hard to explain. So we'll go ahead and use today's date. And write the notes this way. Someone has to remind me to save it at the end of the class, because otherwise you can only watch the video clip, but you cannot actually get to the file, which is, very annoying. Okay. The first thing, what is our problem? So let me just state the problem first, and then I'll let you guys kind of work with me along the way and say, okay, how do we construct or how do we design an algorithm that will do that? Okay, so we want to state the problem first. The problem is we want to find all prime factors of a given number. This number is guaranteed to be greater than or equal to 2, and it must be an integer. Okay, it kind of goes without saying that it has to be an integer, because it doesn't make any sense to find a prime factor of a fractional number. Okay. Do you guys remember how to do that? If I give you a number, say 15, can someone tell me the prime factors of 15? 5 and 3. Very good. Okay, so those are the two prime factors of 15. Sorry?
I couldn't remember the definition of a prime.
A prime number is a number that is wholly divisible only by itself and 1. Yeah, but the prime number itself cannot be 1. 1 is not a prime number by definition. Okay? So it doesn't seem to be a very hard, difficult task. But just because you can do it, like that with smaller numbers does not mean that it is a systematic way that you can, program a computer to emulate. Okay? Because a lot of times we can use tricks that are easy for us, but it's really hard or not worthwhile to code in a program. So the next thing we want to do is to use a few examples. Okay? Use a few examples to make sure we can do it, 1, by hand, and 2, systematically. Okay, what do I mean by systematically? Let's think about an example here. Let's say 36. What are the prime factors of 36? Okay, does 2 pop up right away? Does 3 pop up all the way right away? Why do you know that 2 and 3 are prime factors of 36, like almost right away, instantly? Because it has 6, okay? And also because this is a relatively small number, and we already know it, okay? So that means, when you try to figure out how to do something systematically, you don't want to use anything that is too simple, okay? Because when it's too simple, as a human, we look at this and we use the quote-unquote eyeball algorithm, okay, which basically means we just use our intuition, gut feeling, and stuff like that to solve the problem, which is not useful. Okay, it's not useful when you're trying to write a program. So we try something that's much bigger, so that you will be forced to use a systematic approach as well. Okay, so we start with some number like that. Okay, I just randomly pick some number on the keyboard. Okay, what would be a prime factor of this number? Oh, well, that's not easy anymore. We know 2 is not. Now, how do I know 2 is not a prime factor of this number?
It's not in.
It's not ending with a 2, 4, 6, 8, or a 0. Okay? Now, that is one rule that is easy for us to apply because we use base 10 numbers. But if you are trying to write a program to use the same logic, it is not worth the trouble. Because how are numbers represented in the computer? It's binary. It is in binary. So in binary, it's not even worthwhile to use that trick because you just have to look at the least significant digit. If it is a 0, it is easily divisible by 2, and so on. So the rules of the tricks that we use may not be applicable in binary. So the next thing you do is what? You add up all the digits, right? And see whether that number itself is divisible by 3. That's the trick that we usually do. Is it?
No.
Okay, we have 1, 8, 11, 15, 23, 24. So this number is divisible by 4. Okay. But just knowing that you have 3, one single 3 as a prime factor, does it spell out the rest of it? No. Go ahead.
Is there a reason that works? To add up the numbers?
Yes, there's a reason why it works. Yep.
I mean, it just works.
No, there's a reason that it works. It has to do with the fact that 3 itself is not a factor of 10. If 3 were a factor of 10, then the trick would not have worked. Okay, so it is 3 times something. So now you have to divide this number by 3 in order to find out what that is. So let's see if we can do it by 5, 7, 8, 2, 7. I could be wrong because I just did it, in my mind. Can someone with a calculator do it? Oh, I can use a calculator here. Calculator. Okay. Am I right? That's amazing because I usually screw up on arithmetic stuff. Off by 1, that sort of thing. Okay, so now we have this part here. But I did say that I want to find all the prime factors, not one of the prime factors. So what do we do now? So we want to say, what about this number, right? 3 is taken care of, so the rest is to take care of this number. Now, what about this number? Does it have 3 in it? No. Now, we know that there's no 3 in it because we can apply that trick. We add up all the digits and see whether the sum of all digits is divisible by 3. In this case, it is not. We look at the last digit here. It is not a 0. It is not a 5. So we know it's not divisible by 5. So the next one to try is what? We try it with 7, right? So we'll say go ahead and try to divide it by 7. And let me switch back to my calculator here. So it is divisible by 7. Very good. So this is 7. Okay, so this number is 7 times 8261. So now we look at 8261 and say, can we factor this number? It is divisible by... Is it divisible by 7 again? So the next one to try is 11. Yep, it is divisible by 11. Well, we are just lucky. This is a lucky number. I can tell you why I said that. When I talked about the same topic with one of my classes, I picked a number that has 8 digits, and it turned out to be a prime number. What are the chances that you pick a 7